Welcome to this explainer. Okay, so machine learning. It might sound like absolute magic or maybe some impossibly complex sci-fi concept. But as we're going to discover today, it's really just a fascinating, well-organized set of mathematical tools. Honestly, no PhD required. We just need a good map. Okay, let's dive right into this.
Here is our roadmap for today. We've got 1. Decoding machine learning. 2. The supervised learning split. 3. Essential supervised algorithms. 4. Neural networks and deep learning. And finally, 6. Simplifying data and next steps. This structure is going to be our compass, so we never, ever get lost in the jargon.
Section 1. Decoding machine learning, the foundation. Before we start pulling specific tools out of the box, we really need to understand what we're actually looking at. Machine learning is a field of artificial intelligence using statistical algorithms that learn from data and generalize to unseen data, performing tasks without explicit instructions. Now, the absolutely crucial takeaway here is that it's all about algorithms figuring things out without us having to write explicit line-by-line programming. You don't give the computer a million if-then rules. Instead, it learns those rules just by looking at the data.
Moving on to Section 2, the supervised learning split, the big divide.
So this is where we hit the fundamental fork in the road for machine learning. Think of this massive split kind of like teaching a child. Supervised learning is like teaching a kid with flashcards of labeled cats and dogs. You show them a picture, you tell them the answer, the label, and they learn to predict it next time. You actually have the true labels to train on. Unsupervised learning, on the other hand, well, that's like handing that kid a massive pile of animal photos with absolutely zero instructions and just letting them sort the photos on their own by similarity. Supervised algorithms have the answers. Unsupervised algorithms have to find the hidden patterns entirely on their own.
Now, if we walk down the supervised learning branch, where we already have those labeled answers, we hit another immediate split. And this one is based entirely on the type of data we're trying to predict. If you want to predict a continuous, numeric target like, say, the future price of a house or next week's exact temperature, you use regression. But if you need to assign a discrete, categorical label, like deciding whether an incoming email is spam or no spam, you use classification.
Section 3. Essential supervised algorithms, the core toolkit.
Let's look at the specific algorithms that live on this branch, starting with the simplest. The mother of all machine learning algorithms is linear regression. It literally just tries to find a linear relationship by minimizing the distance between your data points in a straight line, like predicting someone's height based on their shoe size. Pretty simple, right? But if you need to classify something, you use logistic regression. This cleverly bends that straight line into an S-shaped sigmoid curve to predict probabilities. So for example, rather than a straight line, it might predict there's an 80% likelihood of someone being a specific gender based on their height and weight.
Next up, we have k-nearest neighbors, or KNN for short. Instead of fitting some massive, complex math equation, KNN just looks at the closest data points, its literal neighbors, to make a prediction. The real trick here is the variable k, which dictates exactly how many neighbors to look at. It's a really delicate balancing act. Pick a tiny number, like 1, and the model overfits, basically memorizing the training data but completely failing out in the real world. But pick a massive number and it completely underfits, washing out all the nuance.
All right, next is the support vector machine, or SVM. Imagine drawing a line that perfectly separates cats from elephants with the widest margins possible. But what if a straight line isn't enough? That is where kernel functions step in. These functions mathematically twist the data behind the scenes. It's almost like instantly calculating a BMI feature from separate height and weight variables, which allows the algorithm to cleanly slice through highly complex, messy data. Then we have naive Bayes, which is an incredibly efficient algorithm built on Bayes' theorem. And yeah, we call it naive because it makes the wildly false assumption that all words appear completely independent of each other. It's a bit clueless in that regard. But honestly, this simplified assumption makes it computationally lightning fast and incredibly accurate for things like your email spam folder.
This brings us to a really beautiful philosophy in machine learning, combining many simple models to create one powerful, complex model. This is the whole heart of ensemble algorithms, like random forests and XGBoost. Instead of relying on one single decision tree to classify your data, which, let's face it, might make mistakes, you create an entire forest of many simple trees and have them vote together to make highly accurate predictions. It smooths out all the errors and creates a super strong predictive model.
Section 4, Neural Networks and Deep Learning, the Reigning King.
So we are now pivoting to the climax of this map.
Looking at the driving force behind the mind-blowing modern AI you hear about every single day. We just saw how algorithms can predict things when we give them clear features, right? Like height or weight. But what if the computer doesn't know which features to look for? Think about recognizing handwriting. Every single person writes the number 1 slightly differently. The exact pixels illuminated are never ever the same twice. Traditional models really struggle here because nobody explicitly programmed a vertical line feature for the computer to recognize.
Well, deep learning solves this completely through implicit feature engineering. Hidden layers sit right between the input, like raw image pixels, and the output. Without any human guidance at all, the first hidden layer might automatically learn to identify a simple horizontal line. The next layer combines those lines to recognize shapes, and then advanced layers combine those shapes to recognize complete, incredibly complex concepts like human faces. It literally figures out the necessary features entirely on its own. Absolutely wild.
Section 5. Unsupervised Learning and Clustering. Finding order in chaos.
Let's pivot to the other main branch of our map and see how algorithms behave when we have absolutely no labels to guide them. Before we go any further, we absolutely have to clear up a distinction that trips a lot of people up. Classification requires training data with known, true labels. It is strictly supervised. Clustering, on the other hand, finds unknown groups purely based on the underlying structure and similarity of the raw data. It is completely unsupervised. You don't tell the algorithm what the groups are, it explores the data and it tells you.
Let's look at the actual mechanics of the most famous clustering algorithm, k-means. First, the computer randomly throws down cluster centers. Then, it assigns every single data point to whichever center happens to be closest. After that, it recalculates those centers based on the newly assigned points, and it just repeats this loop over and over until everything finally stabilizes. Honestly, it is mesmerizing to watch how elegantly a computer can organize chaotic, completely unlabeled data into tight, meaningful groups just by following those 4 steps.
Section 6. Simplifying data and next steps, the final polish.
To wrap up our map, we need to introduce a concept that is crucial for handling the overwhelming datasets of the real world. Imagine you're trying to predict a type of fish. If you use both the fish's height and its length, well, those features are highly correlated. They basically tell you the exact same thing, which just introduces noise and confusion. Dimensionality reduction algorithms, like principal component analysis or PCA, they shrink these massive datasets. It merges correlated variables like height and length into a single clean shape feature. It keeps the essential signal while ditching the noisy, redundant data, which makes your model vastly more efficient.
And that brings us to the end of our map. See, you didn't need to memorize the underlying calculus or all the complex math. You just needed to understand the landscape and what each tool is uniquely designed to do. So now that you have the ultimate mental map of these tools, which algorithm are you going to deploy to solve your first machine learning problem? Thanks for joining me on this explainer. Stay curious, and I'll catch you next time.